All right. So good morning, everyone. Today's class will be on semantic analysis. Some of the ideas discussed in this course are based on the lecture notes from Alex Icon's compiler's course from Stanford University. So as you know, we have been studying about lexical analysis and syntax analysis for probably 4 weeks. So given an input program, the lexical analysis and syntax analysis modules put together, they check whether the input program has any syntax errors or not. If there are no syntax errors, it's great. So they construct the parser or the syntax analyzer component constructs what is called as an abstract syntax tree. This is what we have seen in the last class, how to construct the abstract syntax tree. And if there are any syntax errors, then those syntax errors will be reported back to the programmer, to the end user. So once this AST is constructed, we can do multiple things with this AST. And one of the important things that we do with AST is semantic analysis, whether the program is semantically well formed or not. So as you know, many of the things associated with semantic analysis, they are context sensitive in nature and they cannot be captured using context-free grammars, and hence they cannot be detected. Any semantic issues in the program, they cannot be detected during the syntax analysis phase or parsing phase. So today in today's class, we assume that AST is given to the semantic analyzer, and the semantic analyzer makes multiple passes over the AST to check if there are any semantic errors in the program. And if there are no semantic errors in the program, then the compilation goes to the next phase, that is the intermediate code generation phase. So if you think about it, even AST is also an intermediate representation. So what happens here though is AST is close to the programming language, but at this level, at this intermediate code generator, it transforms the AST into a sequence of instructions, and these instructions are more closer to the target assembly language. So that's what happens in this intermediate code generator module. And one important data structure that you should make a note of here is the symbol table data structure. We will talk about the symbol table data structure a bit in today's class because the symbol table data structure is required by the semantic analyzer module. It is required by the semantic analyzer module. So what are these semantic checks? And specifically, we are calling these as static semantic checks because these are the semantic checks which the compiler would like to do at the compilation time, not at the time of program execution time. So a few examples of static semantic checks are like, for example, if you have a break statement in C, which is not present in a while loop or in a for statement or in a switch statement, then that break statement doesn't have any meaning per se, in which case we have to inform the programmer that you have a break statement in your program, and that break statement is not enclosed within a while loop or a for or a switch statement. That is one example of static semantic check. And this can be done just by looking at the program text. The second semantic check is so using a variable which is not declared. So every variable that we use in C, you know, it has to be declared before its use. So this is another example of static semantic check. And then, so when we make function calls, we pass some arguments to that function call. And the type of the arguments that we pass to the function call, in the function call, they should match the parameter types from the corresponding function declaration. Like for example, if you are using a string compare function from the string library in C, and if you're passing two integers I comma j, then you should then the compiler should raise an error saying, you know what, so the string compare function is expecting pointers to strings or a character array, but you are passing two integers, so there is a problem. So that kind of type mismatch you should the compiler should report. So this is another example of a static semantic check. And the fourth example here we have is the value returned by a function matches the return type. So for example, here you have the return type is void. Let's assume that the return type is void, but you are returning an integer. So you have a function like this, void add whatever. Okay, but then you are returning something like return x plus y. So you are returning an integer, but the declared type of the function is void. So there is a mismatch. And the fifth example that we have here is the L value of an assignment statement is not a constant. It should be a valid thing. So like for example, we cannot have something like 4 is equal to x. This is not allowed. So this is what is on the left hand side of an assignment statement. It has to be a valid L value. These kinds of mistakes, they may not be quite glaring, but there could be some involved cases in which you may have an incorrect L value on the left hand side. And finally, if you consider, so if you consider programs, primarily our programs does a lot of computation. Okay. And if you consider an expression such as x plus y, the operands of this expression like x and y, with respect to the operator plus, they should be compatible with each other. For example, if x is of type integer, sorry, I didn't write here, x is of type integer and y is of type bool, and maybe we cannot perform a addition operation between integer and bool, in which case we have to say that it's a there is an error in this computation that is happening in the expression that is specified there. The types of the operands are not matching with respect to the operator with which they are connected, and we have to, the compiler has to generate a semantic error. So these are some examples of static semantic checks. And some other examples of dynamic semantic checks, if you think about, let's say if you are accessing an array A of I in your program, you have a loop, and somewhere in the loop you are accessing A of I. You want to make sure that the array access doesn't go out of bounds. It is very hard to come up with a compiler analysis, semantic analysis task which can do this check. It's not possible. Like for example, we could be, you may have something like, you know, this is, the program could be something like for I is equal to 0, I less than n, plus I, and somewhere you could be using A of I. But this n you could be reading from the input. So how does the compiler know what is the value which the user gives for n? And the size of the array could be, you know, maybe 10,000, and the size of the array is something like int a of 1,000. So if the user gives a value of n which is greater than 1,000, then you will end up accessing indexing elements which are not present in the range, and this is in out of bounds array access, which is not permitted. And you cannot do this check at the compile time. So you have to do this check at the execution time. That means we have to generate extra code when we are mapping the C program to the assembly code. What we have to do is we have to, wherever we are accessing the array element A of I, we have to check whether I is within the bounds and then do the access A of I. So while technically it is possible, it generates it's a overhead. It's a runtime overhead. If you want to do this dynamic check, that when we are accessing an array element, so we are that access is within the bounds. If you want to do it at runtime, then it adds to the runtime overhead. Another example of semantic check which cannot be done statically at compile time is when there is a operation such as expression such as x divided by y. At compile time, we don't know what values the denominator y will hold. So again, we may want to do this check at in the runtime, at the execution time, where before this division operation is done, we would like to check whether the denominator is a non-zero value. So while this is doable, again, it adds to the overall runtime overhead. Another example is when this is a very common example, especially when you are learning C programming for the first time, or when the program is very large, you are not able to keep track of how things are flowing. You may end up dereferencing a pointer which is set to null. And checking this at compilation time is very hard. In the case of, like Java or programming languages, like Java and I don't know, maybe Java programming language, like you have these exceptions where when you try to do such things such as this, so an exception will be raised, and you can have a catch statement which will hold that, which will catch that exception. So, but at the same time, it is not possible. It's we can do our best, but it's not a foolproof thing to determine at compilation time itself whether pointer variable holds a null value. So these are some of the things which cannot be done at the compilation time. So that is, they cannot be statically checked, but they can be checked when the program is executing at the time of runtime, but they add to the execution time overhead. So, so that is about dynamic semantic checks. So in this class, we will not study any more about dynamic semantic checks. We will focus our attention on static semantic checks. The first thing in the direction of static semantic checks is what is called as a scope resolution. So, in your program, you have your identifiers. They correspond to different variables that you use in the program. And we would like to match this identifier declaration with the uses. For example, here, if you see there is a statement sum is equal to sum plus I star x, and if you consider the variable sum, so if you go and try to match this sum variable corresponds to which declaration, first you will get an error because the sum variable is used without declaration. So this is an error. And if you look at I, the variable I, it corresponds to this particular declaration. The variable I corresponds to this particular declaration. But you can see that there is one more variable I outside the scope of this for statement. So the scope of the variable I which is present in this here, in this expression, it falls within this for statement. And the scope of the variable I which is declared here, it is within the main statement, but it gets overridden by the I that is present that is declared within the for state. Similarly, if you go and look at x, the variable x, this variable x, it corresponds to this particular declaration of the variable x. But you can see that there is one more variable here, but this variable is hidden uh, inside this main function because of the declaration of another local variable x within the scope of the function. So when we are trying to do semantic analysis, when we are trying to do code generation, uh, intermediate code generation or code generation, the first thing that we have to do is scope resolution. All the variable references that are being made in the program, they correspond to which declaration in the program. And the x here, it corresponds to the global variable x. So the scope resolution we have to do in order to carry on with the semantic analysis or to go to the next step, that is map this sequence of statements or AST to a low-level sequence of instructions. And in programming languages such as C, the scoping rules, these are called as static scoping rules or lexical scoping rules. What it means is the use of a variable. So here when we are using sum, we will be, or like for example, when we are using variable x, we can associate this use of variable x with a corresponding declaration by looking at the program text. So you don't need any other information. Just by looking at the program text, every variable reference, we can say this variable reference corresponds to this variable declaration. That association we can make by looking at the program text only. But there are some programming languages which have dynamic scoping rules. So in these in these programming languages, so the reference associated, when there is a variable is being referenced, the value that that reference corresponds to depends on the particular way in which that execution point is reached. The particular way, what is the call stack when that particular variable x is being used, or what is the enclosing execution environment in which that variable x is being used. So when there are when such is the case, then at compilation time itself, we will not be able to identify or associate a use with a corresponding declaration. Then code generation becomes difficult. Code generation becomes difficult, and there are many other issues you will face. But pretty much all modern programming languages, if you see C, C++, Java, or most modern programming languages, they use static scoping rules. Especially, I feel if the language is being compiled, applying dynamic scoping rules becomes a bit of a pain. Maybe if the language is interpreted, then applying dynamic scoping rules is easy because the runtime environment looks up, hey, the variable x is being used and it has a lot more information, and it can try to identify the use of that variable with the corresponding declaration. All right. So we will restrict our attention to programming languages where static scoping rules are used. Let's keep going. So the next important idea is what is called as a symbol table. So symbol table is a data structure which holds information about all the variables that you are using in your program, their type and their scope information. And this is a so essential data structure that you have to build in order to do semantic analysis. So for example, here on the right hand side, you have the symbol table associated with the program that you have on the left hand side. If you see the top of the symbol table, it has only one entry. That entry says no, so we have, there is a variable x, its type is integer and its initial value is 20. And then if you go to the, and there are two children to this, in this global context, or in this, that is, one is main and the other is fun. And if you look at main, so main has two variables. One is x, which is an integer, and it is initialized to 30. And the other is I, which is also an integer, but it is uninitialized. And then within main, so the outermost scope of main, we are calling it as main.0. And then the next innermost, and then the next scope that we have, main.1, it corresponds to the for statement. And the for statement contains one variable, so I, which is of type integer, and it's not initialized to any value to start with, or maybe you can think of it as initialized to 0 to start with. You can think of it both ways. So when you are doing semantic analysis in semantic analysis or code generation, when we are within this main.1 block, that is within this for loop, so let's say if you are referencing variable x, what you do is you first check whether it is present here in this particular block, in this symbol table block. If it is not present, go to the parent and you check if it is present here. And if it is not present here, then you go to the global context or the global symbol table and see if the variable is present in the global symbol table. Same thing with the fun also. So there is a variable pi, it is of type float and it is uninitialized. So what happens here is when you reference the variable pi, then you can, so that variable pi will be obtained or found in this table. But when fun accesses the variable x, x is not present in this symbol table. So you go one level above and here you can find the variable x. All right. So let's say within this for statement, you have, so this is the for statement. Let me write at a different place. So we have this for statement. I'm just writing this for statement again here. So we have the for statement. And right now it has only one statement, x is equal to x plus I. But let's say it has one more if statement here. And within this if statement, there is one I that is being declared. And let's say there is one more if statement. And again, within this if statement, there is one more I that is being declared. And the whole for statement is closed. So what is happening? Just give me a minute, something weird is happening. Great. So yeah, now if you see the symbol table here, the way the symbol table looks like, you will have something like here. So this is main.1.1 and here you will have one variable I. It could be, it's an integer, and you have another variable, another symbol table, which is main.1.2. You have one entry, that is I is an integer, and this also points to this. So like this, we can construct a hierarchical symbol table. And when we are processing, when we are something weird is happening. Yeah, so again, so when we are processing this if statement, when we are processing this particular if statement, then what happens is we start with this particular symbol table, and so when we refer variable I, then the variable I will be obtained within this symbol table block. But on the contrary, if you refer variable X, from here you go here, and from here you go here, and you will find the variable X here in the main.0 symbol table block. All right. So symbol table is the most important data structure that we have to construct during the compilation process. And actually, one thing I would like you to think about here is, let's say if you want to build an interpreter, okay, it is possible for you to build the interpreter by making an AST pass by building an interpreter pass on the abstract syntax tree. When you are doing that, the side data structure that you need is the symbol table. Like for example, when you are interpreting the statement X is equal to 30, what you do is you go to the symbol table and update the corresponding entry with 30. Similarly, let's say if you are interpreting the statement X is equal to X plus I, what you do is you go and look at the value of X and you go and look at the value of I, and you sum them up and you store the resulting value back in the memory location or in the symbol table entry associated with X. So whether you are compiling, whether you are doing interpretation, symbol table is an important data structure that we have to maintain. So how do we construct the symbol table? And there are a couple of approaches for constructing the symbol table. The first approach is at the time of parsing, it is possible for us to construct the symbol table. We can annotate, we can embed some code in the parser so that when the parser is parsing the variable declaration statements, then it will make a suitable note of that information in the symbol table. So that is one approach. But that approach is bit tricky or involved because your parser could get, your parser code or your parser module could become a bit complex. The easiest is you let the parser pass this information or encode this information in the abstract syntax tree. And then what you do is you make a pass over abstract syntax tree to fill the symbol table. Like for example, associated with a statement such as in the source program, you may have statements such as int x comma y. In the AST, you can have a node such as type node where the left child is int and the right child is ID list identifier list. You can have a AST node like this. So by doing this, the parser, it doesn't do much work. It just creates a corresponding structure in the AST abstract syntax tree. That is, this is what the parser can do. Make variable declarations part of AST. This is what the parser can do. And then later on, what we do is we write a pass over the AST and construct our symbol table. Okay, so this would be a very clean design. Agreed, you may end up making one extra pass over AST, but that should be all right, unless it has very serious performance implications. But I don't think it's the case in modern systems, because we have large amount of memory available. So this shouldn't be an issue. So before we move on, so far we are understanding types not in a formal sense, but through examples. That is, in C programming language we have types such as int, float, pointer, character pointer, integer pointer, pointer to an integer pointer, so on and so forth. So that is how we understand the types, basically through experience. But then if you see, there are different programming languages from C. If you go to C++, you will see classes. You have inheritance and a lot of object-oriented features. So the notion of type in the context of object-oriented programming languages, it is more involved than a programming language such as C. So what we will do is we will try to take a semi-formal view of types. Uh, it's not a complete formal treatment of the types. It's a semi-formal treatment. That is good enough for this course. So if you think of type, a type represents a set of values. Like for example, if you think of unsigned integer type, unsigned int type, if you think of this, then it represents all the numbers in C from this, in this range. All the unsigned integers, all the positive numbers in this range. These are the set of numbers which correspond to unsigned int type. Similarly, you have the float type, you have the double type, so on and so forth. And every type corresponds to, associated with every type, there will be a set of values. Not only a set of values, a set of operations on those values. For example, if you take a pointer, you cannot take square root of a pointer. It's not a valid operation on a pointer, but square root on an integer is allowed. It makes sense. So like that, for every type, there are set of valid operations that are permitted on that type. So now let's take this example of this assembly language statement, which means add the contents of register R2 and R3 and store it in register R1. This is what this assembly language statement means. But the interesting thing is, by looking at this assembly language statement, we doesn't know what is the type of the values which these registers are holding. And the processor also doesn't know anything about the contents of these registers. All it does is it knows, so it has to take the 32-bit value that is present in register R2 and the 32-bit value that is present in register R3, and it has to add it up and store it in register R1. That is the semantics that is given by the processor. But the registers R2 and R3, they may contain, and they may contain unsigned integers. They may contain signed integers. Or they may contain, like for example, R2 may be a pointer and R3 may contain the constant 1. So like for example, when we are doing arithmetic such as PTR is equal to PTR plus 1. So what these registers hold, the type of the values that these registers hold, just by looking at the instruction, we don't know anything about it. But hopefully the assembly language programmer who is writing the program has these things in his mind, that hey, by the time this instruction gets executed, this is the data that will be present and this is the type associated with this data. So the programmer needs to have a mental model of what is happening in the assembly language program. Unfortunately, this is what makes it very difficult to understand assembly language programs, because the mental model which a programmer have it's not very explicit. It's not at all explicit in the program. If someone else looks at the program, he doesn't understand. No, it's very hard for him to understand that program because he doesn't have access to the mental model of the original programmer who wrote that code. So he has to really go through the code very carefully and trace how the data flows to figure out what is happening. So one way to solve this problem is we can possibly document the code by saying, in this, when the processor hits this instruction, R2 contains the variable PTR and R3 contains a constant one. This kind of documentation in the form of comments, the assembly language programmer has to provide. So an important idea that is coming out here from this discussion is the type system. It helps in two ways. The types help in two ways. One way is it helps the compiler. Okay, like for example, if you have x is equal to y plus z, depending upon whether y and z are integers or whether they are floating point numbers, the compiler has to generate the appropriate addition instruction. Like for example, if it is a plain if y and z are integers, the compiler can possibly generate an instruction such as this. But on the contrary, if x, y, z are integers, if x, y, z, if they are ints, then the compiler can generate an instruction such as this. But on the contrary, if x, y, z are float, the compiler may have to generate an instruction such as this, FAD, floating point add instruction. So the type information helps the compiler in deciding what to do while mapping this code to target assembly. So that is one. But there is a second important thing. It helps as a documentation of the program, makes the program more readable. When someone else reads the code, just by immediately looking at the type of the variables x, y, z, he will get some idea about what these variables, what is the purpose behind these variables. At least he'll get some idea. It helps in documentation. It helps in program documentation. Let's keep going. Yeah, so as I said, certain operations are legal for values of each type. Like for example, if you are dealing with pointers, the square root operation doesn't make sense, and the compiler has to emit a semantic error that you are trying to compute the square root of a pointer and it's not permitted. And the goal of type checking is to ensure that operations are used with the correct types. This is what this is part of semantic analysis phase. Type checking is part of semantic analysis phase. And when we are designing this programming language, we have to specify the type system clearly. And a language type system clearly says, a language's type system clearly specifies which operations are valid for which types. Which operations are valid for which types. So like when you are writing a document, a language manual, in the language manual, you need to have a clear description of the language's type system, which consists of all the possible types and the operations that are valid on these types. And the compiler uses that information in order to enforce and enforces them in the semantic analysis module. Yeah. I cannot hear you. Maybe I'll take your question a bit later. There are three kinds of languages. One is statically typed languages, dynamically typed languages, and untyped languages. So in untyped languages, that is machine code, assembly or machine code, there is no type checking at all. So I'm back. So there are three kinds of languages. Untyped languages, that is assembly language code. When you write machine code or assembly code, the assembler just maps those assembly instructions to equivalent machine code and absolutely no type checking happens. And there are languages like C, Java, where almost all the type checking happens at the time of compilation itself. The type of every variable, every expression, every sub-expression, you know, at the time of compilation itself. These are called as statically typed languages. And there are some languages such as Scheme where type checking happens as a part of program execution. And even Python is an example of such a language where type checking happens at the time of program execution. So important thing here is in programming languages such as C, where type checking happens at compilation, lot of errors will be caught at the time of program compilation itself. So that is one big advantage for statically typed programming languages such as C, where if there are any problems in the program, they will be caught at the compile time itself. And this has another advantage. So at runtime, there will not be any checks. So there will not be any runtime overheads. So these are the advantages of static typing languages where static typing is used. And dynamic typing languages such as Python, so they are easy to write. It's relatively easy to quick. It is relatively easy to write a Python program. You don't write many lines of code. You immediately start typing in few lines which are necessary, and then you can get your job done. But in my experience, so this is what I found with respect to Python. When I compare, I did good amount of programming in C and also in Python. So Python is a dynamically typed language and C is a statically typed language. So when we write C programs, usually in order to get a small job done, you have to write many lines of code. But in Python, you require less lines of code to do the same job. So that's the reason why it is good for rapid prototyping. But I am not sure that this rapid prototyping feature is coming because of the dynamic typing feature, or because Python has other language features which are rich and lots of libraries that are available. So whether the rapid prototyping ability of Python, whether it is coming because of dynamic typing or because of some other language features and libraries available, I am not sure. When we compare it with C programming language. Of course, dynamic typing also has impact because when I start thinking, I don't need to clearly think about the type of the variable that I am using, etc. I simply start writing and then let the interpreter decipher the type of the variable. I don't pay too much attention. So that helps a bit, but I'm not sure whether how much the dynamic typing facility itself makes rapid prototyping easy. That's number one. This is, I'm talking from my personal experience rather than what is there in the books. The second thing, the big problem that I found with Python is there are two problems which I found with Python. One problem is reading a code that is written in Python. I'm talking about the code written by myself a year back. If I go and read that code, then I don't have the types of the variables. Then I have to really search and go through the code to figure out, hey, what is this particular variable holding? What kind of data this particular variable is holding? It's not at all clear. So I have to go through the program flow and in order to figure out what a particular variable is holding. But on the contrary, this when I go look at a C source code, let's say if I want to read a function, the first thing that I would do is, you go and look at the function signature, you know the parameter types and you know the return type. So you get some idea about what that function is doing. And then you go look at the types of various variables, and all of them, they tell something about what that function is doing. And this is, I find this is kind of missing in Python programs, which makes reading Python programs a bit hard to read. That's number one. Number two, which is more serious problem, is I have written a program, let's say, or you or I have written a program. Let's say you wrote a program for no, for training some machine learning module, and it took 1 week uh, to train a network. And at the end of it, you are you learn the network, you are trying to store that the weights of the network in some particular data structure. And what can happen is, at that point in time, there could be some you could be using a statement where types are not matching, and the whole program will crash at that time, saying, you know what, so there is this type problem and I am not able to carry out this statement. So it requires a whole 1 week of your time gets lost, because everything is done. Finally, the last point that you want to do, that is, you want to dump something, and at that time you have hit a statement which is not appropriate, and you could have easily caught it if the interpreter did the static type checking before. And this I am not making up, and this happened to me when I am working on a couple of compiler projects before. So so these are the two practical things which I found uh, in uh, in practice. That is, reading the code is hard in dynamically typed languages such as Python. Number two is, you may end up catching errors, bugs very late in the program execution time, and that could be very costly for you. That could be very costly for you. Yeah. So, but if you on the flip side, if you think about C or Java, so where the languages are statically typed, most of the time we really don't pay attention to these types. We kind of force the compiler to do what we want to do by casting, like from one type to another type. And so you compile the program, the compiler gives a warning on error. Instead of carefully thinking how to handle that issue, what do? You end up saying, the compiler says there is this error, and then instead of thinking about what is the right approach to solve the problem, you'll use some kind of typecast operator such as this, which may not be the right thing to do. So this is what happens in statically typed languages. But whereas when we think about dynamically typed languages, so there what is happening is, as I said, there are problems in program debugging, and there are performance problems also, because you end up doing type checking at runtime. So there are issues there. So you want to do some kind of partial static type checking in these in Python programs also, for two purposes. That is, number one is program debugging, the other is optimization. You want to make the program run faster. So, like for example, if this is the set of variables that you use in a Python program, you can possibly use a static type checker, and you can use a static type checking algorithm, and possibly able to say confidently all these variables types. But there could be a small fraction of variables which are hard to handle, which are hard to uh, find their types. We leave them out and we try to work with these variables and use this information to the best for program optimization and debugging. So there is a lot of research happens in this space. And then we have these two things. One is called as a type checking. Type checking is the process of verifying fully typed programs. And type inference is the process of filling in missing type information. It seems these two things are different, that is type checking and type inference. I am not an expert in this space. So I don't know the subtle differences between these two things. One is type checking and other is type inference. So coming back to what we are doing, coming back to C-like programming languages. So it's, it's extremely easy to handle C-like programming languages by and large when we compare it with programming languages such as C++ or Java, which are object oriented in nature. In C, like for the particular, for mini C programming language for which you are building a compiler, once you construct an AST, it is very easy to find uh, the, the type of various expressions, variables in the AST. So what do you do? So you have a left subtree here and you have a right subtree here. You find the type of the left subtree and pass it to the root, and you find to the parent, and you find the type of the right subtree and you pass it to the again to the parent. And here, depending upon the operator, you check whether these two types are compatible with each other. Like for example, here, if int is coming from here and int is coming from here, it is all good. But instead of int, if bool is coming here, you may want to generate a type error. But instead of bool, if you are getting a float, then you may want to cast this int to a float, because that is what the language rule says. That is, if you want to add an int with a float, you want to convert the int variable to a float variable. And you may want to slightly modify this abstract syntax tree in order to reflect that fact. You may want to modify it, or you may need to find a different way of doing it. So you will say float and then this whole subtree. The original subtree remains the same. Let's say this is T1, this is T2. So these two trees remains the same. This is T2, T1 remains the same. But the left-hand side, you introduce a new node called as float. What this node does is, whatever the int value that is coming from its child, you cast it to float and pass it as an operator to the root node, to its parent node, which is performing addition operation. So while doing semantic checks, you may also want to slightly modify the AST to handle cases such as this. So this is all about, this is a very simple way. So for C-like programming languages, doing type checking and inference is relatively easy. But if you go for C++, where you have classes, and then you have inheritance, and then there is polymorphism, and then we have method overloading, operator overloading, and then you have virtual functions. There are so many features there. And then there are templates, types, when you can you have generics, you have templates. So when all these things come into picture, then the complexity of the semantic analyzer module becomes pretty hard. It's not the same, it's not as easy as what we are seeing on this slide. But none of these ideas we will cover in this course. We will just be happy with doing type checking and inference on C-like programming languages. But I would like you to keep in mind, when we go to object-oriented programming languages with all these features, semantic analysis becomes much more complex. It's not the same. So what I will do is I will conclude this with by showing you one program. So this is the program that I have written just to see. So this is a Python program which takes input from the keyboard, and like int text transforms. When input is read from the keyboard, it is read as a string. The int text function, it transforms this into a integer. This will be turned into an integer, this inpex. And if x is greater than 0, then y is equal to 1. Otherwise, y is equal to some string blah. And then here we are incrementing by y is equal to y plus intex. And finally, we are printing. So here I will, yeah. So if we compile, if you run this program, Python 3 test.py, if x is equal to 2, then control goes to line number 4, and so on line number 4 y is equal to 1, so y becomes an integer, so line number 8 is a valid statement. On the contrary, if we give y is equal to x is equal to -3, then then what happens is control goes to line number 6. On line number 6, y is assigned to a string. So by the time we reach line number 8, we are adding a string to an integer, and there is a type mismatch. So this the interpreter is saying that there is a type error. You cannot add a string to an integer. So on line number 8, we cannot at program at compilation time, we don't know whether y is an integer or whether y is an integer or a string. So because of that, we cannot say for sure that things could go bad on line number 8. So you have to wait till that particular flow of execution comes, and the interpreter says, hey, you know what, this particular program flow is wrong, because when you take this program flow and when you hit line number 8, or when you reach this execution point, in this particular expression, there is a type mismatch between two operands. One more thing I would like to mention here is so just before when I am writing this code initially, by accident I just wrote y is equal to y plus x, and then when I gave positive input, this program so in this particular case, when we run this program, whether it is positive or negative, it gives an error, because even if x is equal to positive and control goes to statement 4 and then control reaches statement 8, so when control reaches statement 8, y is an integer but x is a string, because I didn't cast that string x into an integer x. The point I want to make here is, let's say the code that is present here, if it takes, let's say if it takes 3 hours to execute, and then after all this execution happened, and it comes here, and then there is a small problem, and then the program crashes saying, this is sorry, there's a type mismatch, then all these 3 hours of work is gone. And this happened to me few times. So this is the big complaint I have on Python kind of programming languages. You have to be really careful so that the work that you did, it's not lost. All right. So with this, I conclude today's lecture. And if you have any questions, I will take